welcome to Classical Mechanics 2. In this video, we'll be exploring drag and air resistance. Drag is a force that depends on the velocity that an object is traveling, and it acts in the opposite direction of the particle's motion. Drag is a complicated force. It depends on the shape of the object that's moving, it depends on the nature of the medium, and on the interaction between the medium and the object surface. To get a better handle on it, let's use a tried and true trick. We're just going to tailor expand the force for small velocities. This gives us a power series in terms of velocity. For now, let's keep the two lowest terms: a linear term, F linear, and a quadratic term, F quad. The linear term describes the interaction between the object and the viscosity of the air. It has coefficient B equals beta times the diameter of the object d, which has units kilograms per second. At standard temperature and pressure, a sphere moving through air has beta equal to 1.6 times 10 to the minus fourth Newton seconds per meter squared. The quadratic term comes about because the object must accelerate the mass of the air in order to move it out of the way. It has a coefficient gamma times the diameter of the object squared, which has units kilograms per meter. At standard temperature and pressure, gamma is equal to 0.25 Newton second squared per meter to the fourth. So how do we know if a particular system is dominated by linear air resistance, quadratic air resistance, or both? We can do this by looking at the ratio between the two terms. F quadratic divided by F linear is equal to 1.6 times 10 to the third seconds per meter squared times the diameter of the object times its velocity. Thus, if this dimensionless quantity is very small, linear drag dominates, and vice versa. Here are a couple of cases to consider. First, we have a baseball that's 7 centimeters in diameter traveling at velocity 5 meters per second. This has a ratio of quadratic to linear drag of about 600. So that's pretty strongly in the quadratic regime. Next, imagine I sneeze. A sneeze has droplets that are approximately 5 microns in diameter, and they travel pretty fast, about 50 meters per second. This has a quadratic to linear drag ratio of about 0.05. Since this ratio is of order 1, both quadratic and linear drag forces are important to the system. Lastly, let's consider a bacteria. Imagine for a moment that bacteria can swim through air. It has a diameter of about 2 microns, and it swims at about 30 microns a second. This bacterium has quadratic to linear drag ratio of about 10 to the minus 7th. So the quadratic term is negligible, and we only need to consider the linear drag term. Said another way, the bacterium is interacting with the viscous nature of the air. Let's look at a couple of examples of linear and quadratic air resistance. First, imagine we have a ball that's falling under the effects of gravity. It is subjected to linear drag. What is its trajectory as a function of time? Here's a free body diagram for the system. It has a gravitational force and a drag force. From the statement of the problem, the ball is moving downward, and we know that the direction of the drag force must oppose the direction of motion. When the gravitational and drag forces are balanced so that the ball feels no net external force, it travels at a constant speed, which we call terminal velocity, which is given by mg divided by b. Next, let's write down the equation of motion for the system. My double dot, which we're going to write down as mv dot, is equal to mg, which is the gravitational force, plus minus bv, which is the drag force. Let me rearrange the terms here by dividing both sides through by m and pulling out a factor of minus b from the right-hand side. So this gives me dv by dt is equal to minus b over m times v minus mg divided by b. And we just said that this term here is the terminal velocity. So this is equal to minus b over m times v minus the terminal velocity. So now this is a separable equation. Let me do a quick change of variables to make this a little easier to solve. Let me call this term here u. Now my differential equation is du by dt is equal to minus b over m times u. Let's collect terms and integrate. I end up with the integral from u at time 0 to u at time t of du prime divided by u prime is equal to the integral from 0 to t of minus b over m times dt prime. Integrating this gives the natural log of u of t divided by u of 0 equals minus b over m times t. I can take the exponential of this and plug back in for the velocities, and I get vt minus v terminal is equal to v at time 0 minus v terminal times e to the minus b over m times t. To find the trajectory as a function of time, I can integrate this once more. Let's sketch to see what this looks like. I have one term that decays exponentially and one term that's a constant. So here's the initial velocity, and then I exponentially decay down to the terminal velocity. So if any of you have ever been skydiving, this is what you would have felt. Our next example is about quadratic drag. Consider a droplet that is moving horizontally subject to quadratic drag. What is its trajectory as a function of time? This is its free body diagram. The only force acting on it is drag. The equation of motion then is mx double dot, which we're going to write as mv dot, is equal to minus c times v squared. This again gives us a separable differential equation. So let me group terms and then we can integrate. So we have an integral from v at time 0 to v at time t of dv prime divided by v prime squared. And this is equal to the integral from 0 to t of minus c over m times dt prime. So this gives me minus 1 over v of t minus 1 over v naught, which equals minus c over m times t. And I'm going to call the time scale m over c tau. Now to solve for velocity as a function of time, I have v of t equals v naught divided by 1 plus t over tau. Now I can integrate this once more to find position as a function of time. So I have x naught plus v naught times tau times the log of 1 plus t over tau. So now let me plot both of these. For velocity, I start at v naught and it decays to 0 as 1 over t divided by tau. So this is slower than the exponential decay that we just saw. For the trajectory, let's start at position x naught, and this function now has logarithmic growth. So eventually I'll be able to reach infinitely far away, but it'll take me logarithmically long to get there. The last thing I want to mention briefly is what happens with drag in 2 dimensions. Here's an equation of motion. mr double dot is equal to mg minus cv squared times v hat. Here I'm picking quadratic drag, but this can be any type of drag. The important part is that there's a scalar function of v and that its direction opposes the direction of motion. We can rewrite the vector v hat as the vector v divided by its magnitude. That means our drag force is equal to minus c times the absolute value of v times the velocity vector. So now that I've written it that way, it means I can split this up into component form a little bit more easily. In the x direction, I have mvx dot is equal to minus c times the magnitude of the velocity times the velocity in the x direction. And I can expand the magnitude of the velocity as minus c times the square root of vx squared plus vy squared times the velocity in the x direction. Likewise, for the y equation of motion, I have mvy dot is equal to mg minus c times the magnitude of the velocity times vy. So this is equal to mg minus c times the square root of vx squared plus vy squared times the velocity in the y direction. So this is a fairly nasty set of equations. Both of these two equations depend both on vx and on vy. So this is a coupled nonlinear set of first-order equations. And we're going to talk about how to solve these a few videos from now. In the next video, we'll take what we've learned about drag and apply it to oscillations. Thanks for watching, and I'll see you next time.